So I guess you can all see that, okay?
Yeah, it looks good.
That's great. Thanks, Emily. So yeah, we're going to get straight into it and discuss the advantages of using bio-based insulation in modern construction. And this becomes more important, as we know, with the revised Energy Performance of Buildings Directive. We'll soon require the calculation and disclosure of buildings' embodied carbon from 2030 for all buildings and from 2028 for public buildings. So it's important that we understand the carbon impact of our materials. So it's becoming more and more essential. So that'll be the theme and structure of today's presentation. Just a little bit about our company before we get going. I won't dwell too long on it, but we're a long-standing company where our origins go back to 1906, the McCann family. And over the century, we've really evolved into two large teams, one based in Ireland and one based in the UK. So we've been, as Paul mentioned, we've been supplying innovative building solutions, low carbon materials, high performance building technology to the Irish market and to the UK market for over 20 years. And over that time frame, we've seen partnerships grow with many of the leading European brands, some of them that we'll discover today in more detail. So for example, Gramitherm, grass-based insulation, is a recent partnership with Ecological building systems. So we've been helping to bring that to the market, popularize it, train people on its use and its advantages and so on. So some of these products you'll see today. We try to be very active, not just with MMC Ireland, like the CPD we're delivering today, but we have many other membership associations as well. So we try to contribute because our mission is to support a better built environment. So we want to contribute to this sector whenever possible. Climate action is really driving the need for a change, and there's a growing need to, as I said at the beginning, to address embodied carbon and other associated emissions in the built environment. So with that in mind, we have to think about what we're building from. And Ireland's climate action plan that I showed a moment ago, it's setting an ambitious target for us to achieve a 51% reduction in overall greenhouse gas emissions by 2030 and sets out a path to reach low carbon emissions by 2050. But timber is recognised as a key material that can help us meet these challenges. So if we're going to build from timber, then it's also important that the installations we use and that the technologies that we're promoting are consistent with those types of principles. So architects and designers are going to more and more be required to specify low carbon construction methods and even low carbon cement material as far as practical moving forward. So you're seeing big shifts in the industry and a lot of changes in this area. We're also trying to move towards a more circular economy where we're reducing waste, and instead we're trying to promote the reuse of materials. But a big problem we have, if you take these figures taken directly from an IGBC, so the Irish Green Building Council, they published a Circular Ireland roadmap last year, and in it, this is one of the key statistics in the report, which you can download, that 97% of materials flowing through the Irish economy are from virgin sources. So if that's the case, then we're not doing very well in terms of circularity or reusing materials. So if we have such a heavy amount of virgin material moving through the Irish economy, we have to carefully select the material that we're using in construction. So we can do that by using EPDs, or environmental product declarations. It helps us to look at this virgin material. It helps us to determine, what, if any, the impact of the material may have on our buildings. So most manufacturers now declare environmental performance of building products in this way. And as I said, they're not the silver bullet, but they can be used as a frame of reference for building life cycle assessments. Here's just a quick example for you. If you take the EPDs for two products on the market, Thermofleece Cozy Wool supplied by Ecological Building Systems, compared with conventional stone wool thermal insulation that would give you a similar U value. The Cozy Wool, it just by comparison of global warming potential alone, performs about 28 times better, apologies. So just on that basis alone, if you get the same U value, but it has a lot less environmental impact, there's great cause there to be potentially using something that can benefit not only the agricultural sector, but also the environment, as well as building performance. So it's not just about the materials you supply, but in Ecological Building Systems as well, we also try to promote low carbon construction techniques and technologies. Eco-Cocoon, for example, would be a recent partnership that we've, a strategic partnership to try and promote low carbon construction at scale. So if you take the construction technology in mind here, Ecological, which is a load-bearing twin-stud timber frame, it's just filled with compacted straw. It's not treated, it's just pressed really tightly. Then it goes into a big machine, it's lifted in by robots, and it gets a haircut. It gets a very nice, precise trim where you end up with a very consistent panel, very consistent U values, very consistent performance. It's 89% straw, 9% timber approximately, and the rest is about 2% fixings. So wood and straw in these panels naturally capture and store atmospheric carbon through photosynthesis during the growth phase. And a lot of insulations do this as well. Things like wood fibre, things like hemp, jute, etc. You get a lot of carbon sequestering going on. So when you combine a low carbon construction technique like this with a low carbon insulation material, you get many of the advantages that we're trying to achieve for Ireland's Climate Action Plan. So here are some of the construction techniques that you may or may not be familiar with. You can apply sustainable wood fibre insulation to mass timber CLT, for example, on the top right hand side. Or you can blow in a natural insulation like blown cellulose between timber frame studs, and you can clad the outside in wood-based insulation tongue and groove products in the top central image. You can take the same technology and apply it to a roof. Every building in the world has a timber frame on it sitting on top of it. So the roofs can be naturally insulated, enhancing the performance of the wooden technology that's already in place. Or you can go for something, more ready-made, like the Ecological straw wall panel system, which comes with its insulation in it. But if you look at the graph in the center of that slide, the graph shows that most carbon reducing potential occurs in the early planning stages. You can reduce a lot of, this is taken from a World Green Building Council report, which was, I think it was 2023, if I'm not mistaken, the report came out. But it shows in this very clever graph that in the early stages, if you move left on the x-axis during the planning phase, if you do nothing at all, you can save a lot of carbon, obviously. But if you have to build something, then build less and build cleverly. And building cleverly is where we can make good design choices to affect carbon in the atmosphere, because the built environment is associated with about 39% of global emissions when it comes to climate pollution. So really, by carefully selecting what we build from, we have an opportunity to reduce this impact. So natural fibre insulation goes a long way to doing this. It doesn't need to be overly complicated. Natural fibre insulations are made from organic materials like wood, fibre, hemp, wool. The fibres there are then mechanically processed. They're not chemically altered. They keep them as natural as possible. The amount of processing really just varies by the different types, as there does the addition of different fibres and binders. A lot of them use recycled polyester binders, so it also promotes circular economies as well. Most of these natural fibre installations are sourced as byproducts from other processes. For example, the timber sawmill industry has a wood chip waste, and that wood chip is turned into wood fibres of varying densities, wood fibres for roofs, flexible wood fibres for rafters, blown wood fibres to blow into stud-works and cellulose and things like that. So they all have low embodied impact, and a lot of the production takes place in the UK or Europe. So we supply a lot of these on the market in Ireland. We supply wood fibre, we supply hemp, we supply cellulose, we supply wool, we supply grass-based insulation, we supply straw wall panel systems, and a lot of them share similar attributes. When you look at the attributes that they have, without reading the screen for you, they tend to perform in various ways, with the main things being how low embodied carbon they are, how circular they are by design, and how they manage and balance moisture in buildings. They're really, really good at, well, breathing would be just a way of thinking about them, but they're very, very good at balancing excesses in humidity when required. So they're very friendly within timber construction. They suit timber construction very, very well. They're straightforward to install. They can be overcomplicated, but most ordinary people can install this type of insulation. You don't need specialist equipment or safety gear. They are a bit more expensive than the conventional alternatives, because while it's niche, it'll always be more expensive. But as the popularity grows, you should see the distance between the two of them closing significantly. Over COVID, when chemicals were hard to get, when a lot of petrochemical-based insulation companies were struggling to get those ingredients that they need, the prices of those products were rising pretty much daily. Whereas the natural fibre products that were being grown in the ground throughout Europe, the prices were more or less consistent across Europe, and they were only being affected by transport costs, really. but overall the costs were much more stable. So if you're using a natural fiber insulation like this, you can see what its advantages are. Irregular stud spacings and site tolerances kind of make it difficult to use boards and stuff like that. Whereas flexible insulators like these, just to take, for example, Gutex Thermoflex, they're designed to friction fit into these spaces, allowing it to adapt around framing and surfaces, maintaining close contact with the frame itself. They're really easy to press into things, in other words. Just to give you an idea of what they're good at in a quick snapshot, because we only have an hour to get through quite a lot of context. Here's a good report that it's independent from Ecological Building Systems. It's from the Alliance for Sustainable Building Products, produced in 2025. And it's a really good read. It's a good guide and explains, like many of the terms we're using today. The first column in the table with the one underneath the natural fiber heading obviously belongs to natural fiber, and it shows mostly green boxes, indicating a high benefit in each case with a few exceptions. So natural fiber insulations tend to have a lot of benefits when compared to conventional fiber insulations. If you look at it versus mineral fiber alone, mineral fiber, there's nothing wrong with mineral fiber, but if you just want to look at its benefits, you could say it has much more thermal mass than mineral fiber. It has a much better ability to buffer and safely store humidity. It's much more renewable and it's less likely to impact your air quality. So its benefits are much more high-ranging. And then if you look at the natural fiber spectrum, if you look across the board at all the natural fiber products, they have different things in common. I just take a couple and I'll showcase it just to prove it. But if I look at Gramitherm, one of our latest partnerships, apologies for the pie chart, there is a color there that's misleading. The orange section should be purple on that pie chart. But just to give you an idea, it's primarily produced from grass. The grass is taken from parks, canals, grass verges. It's not cultivated grass. So this grass is really respectful to biodiversity. It's grass that's mowed by city councils and things like that. And even the mowing height and times are really carefully planned. So then the dry grass is combined with recycled jute fibres. So you see the dried grass there on the left, and you see the recycled jute fibres arriving in the big sacks and a handful of it there. And then by incorporating renewable grass fibres and recycled jute, that's supporting a circular economy as well, because it's taking that jute waste, like cocoa bags and things like that. So the grass is no longer a food source because the digestible liquid component of the raw grass has been removed during the production. So rodents wouldn't be able to digest the cellulose. And that's also true for straw as well. Once the wheat is gone, once the food source is gone from it, it's just basically mini trees, it's little sticks. So they no longer have an interest in consuming it, in consuming the product. So just some figures from the EPD of this product. The natural grass fibre cleaned without any nutrients is about 70% to 75% of the mix. The jute fibres then from the recycling of jute bags containing coffee beans and things like that, that's about 20 to 25% of the mix. And then there's a low melt recycled polyester fibre. So that's just completely recycled polyester content. That's used as a binder to help bind it all together and keep it kind of consistent. And then they use it's like a baking soda salt mix for flame retardant. So that's added to a lot of natural fiber products as well. So it'll give you an idea of one of the natural fiber products. And then what it's good at is generally consistent across all the natural fiber range. So if you look at what these things are really good at, here's just a graph taken from one of the tests that was conducted. So the test standard in this case, if anyone wants to know that information, is EN12571. But there are various other tests conducted as well, but that's just one of them. So that's one of the testing standards used. This would just be, a snapshot of its capability at varying humidities. So if you move from left to right on the x-axis, you can see that as the humidity gets higher and higher and higher, maybe that's inside a construction. That could be 100 mil deep into a 220 mil stud. As the humidity gets higher relative to the temperature inside the space, the product is able to absorb more and more and more of that humidity. It has really, really strong hygroscopic properties, which is great at balancing excesses in moisture. It's also very good at desorbing. So while it can absorb that excess in humidity, safely buffering it, Other things that are well known for that would be wood fibre and cellulose and so on. It's also great at desorbing as well. So when conditions allow, when drying is more favourable in various directions, it's very good at releasing it too. It doesn't hold on to it. It doesn't. It's not a permanent storage. So a lot of natural fibre installations are really, really good at that, and they do so without any harmful emissions. So there's no off-gassing when it comes to these natural products. While there isn't any national guidelines for volatile organic content, there is some standards out there that people point to, like WELL. And WELL is a performance-based system for measuring the impact of the built environment on health and well-being of people. So many people will use WELL as a kind of a, well, here's what WELL says. Okay, so many building materials are known to off-gas VOCs, like polyurethane-based products tend to off-gas, depending on how they're made. A lot of them use blowing agents during construction or during production. And those blowing agents can be released slowly over time, can add compounds to the air we're breathing. But if you use the WELL guidelines, and if you say that 500 micrograms per meter cubed is a safe threshold not to exceed, okay, so they suggest that a healthy material would be a value lower than 500 micrograms per meter cubed. Well, then just look at the emissions that's coming off something like a natural fibre insulation, and you can cross-reference that and see that after 28 days, 17 micrograms per meter cube were measured. So 500 was a safe level. And if this test report gives you an A+ for having less than 1,000, well, then 17 is surely a safe value to use. So this ensures that if you're using natural fibre installations, that you end up with healthier indoor quality, and air quality, of course. It's like having good water quality. We all want to be breathing clean air, just in the same way as we want to be drinking clean water. So it's hard to see it, but making sure we surround ourselves with the non-harmful products and non-harmful materials will make sure we're not making conditions like asthma any worse. So the indoor environment benefits greatly from selecting products like these. Then on a technical capacity in buildings, of course, these things are very important as well. So it's great at absorbing sound. You could take any natural fibre product, you could put it into intermediate floor spaces or separating walls between bedrooms or whatever, and its ability to dampen acoustic noise, or just to absorb noise energy, is very well known. So you can see here by this graph taken from its technical details that if you run down the little graph on the side, at a frequency of 1,000 hertz, it's capable of absorbing, or its noise absorption coefficient is 0.99, which is 99% of the sound energy hitting it. So it's capable of absorbing all that sound because it has, and similar to wood fibre and other natural insulation products, it has great dynamic stiffness. It's very flexible, yet it's kind of semi-rigid. It has a lot of texture and surface area. It's brilliant at absorbing noise. It's a great buffer to absorb noise. And we actually have a sound test in Ecological Building Systems where we have 3 various boxes made up of different insulation types: stone wool, XPS, wood fibre. And we have a speaker inside all 3 of them. And you can turn up the noise based on whatever music you want to play, and the wood fibre really deadens the noise. It really, really absorbs that energy, whereas the other 2 may as well not be there. It just floats through it. So these are some of the natural advantages that a natural fibre insulation product can offer. And again, as I said, I could take a look at a different product, for example, IndieBreed Flex, which is a hemp and jute product that we're supplying currently. And I can just look at its constituents and its makeup and its density and its thermal conductivity, and I get a very similar outcome. So it nearly becomes a situation of, what do you prefer the most? Is it grass? Is it hemp? Is it what's your preference? Because natural fibre insulation, it's kind of hard to pick a favourite. My personal favourite is the sheep wool. I like the sheep wool myself, but I'd be very happy to be surrounded by all of it. None of it minds. And again, just in the same way that the others have salt added to it for fire protection, this one also has a 1% sodium carbonate added as well. So there's a lot of similarities between these various products. And then their thermal conductivity is pretty similar as well. There is a range. I mean, there may be 10% difference from one to the other overall, but just take, for example, how they perform in construction, because U values are important. Thermal performance, over the next few slides, you'll just see that there's a similarity between them all as well. If I take a passive eco wall frame, so if I get a timber stud spaced at 600 mil centers and I blow in wood fibre into the stud, And then if I clad it with 60mm wood fibre board on the outside and create a rear ventilated facade, I get a U value of 0.12. That's with the inclusion of a 40mm insulated surface cavity inside. And all of that frame is all blown wood fibre, flexible wood fibre, and dense wood fibre. So 0.12 is very achievable with a relatively conventional frame size, 220mm frame. So that's passive standard of performance with natural insulations in a cleverly designed way. If I take the Eco-Cocoon straw wall panel system, depending on the straw wall panel that you use, I can take a 300mm panel and add 60mm of Gutex to it, and I get a U value of 0.15. Or I can take a 400mm panel and add 60mm of Gutex to it and get down to 0.12. So the values and the performance are very, very similar. This just happens to be a pre-insulated timber frame packed with straw. So you can see that natural insulators share a lot of similarities overall, especially how you build and how you use them as well. And then if I take it away from a wall and I stick it on a roof instead, yeah, the same principles applies. Really, the size of the rafter will dictate most of the U value because that's where the best insulator will go. So if you have a larger rafter, if you've got a rafter of 220 versus a rafter of 140, you'll see there's a big jump in U value performance because most of the insulation is going into that space. But overall, these natural insulators can do pretty much anything that conventional insulators can do as well. They'll never perform to the same thermal quality alone, just if you're looking through that lens only as something like PIR, for example, because that's just a U value race. But if you're looking at it in terms of thermal mass or moisture balancing ability or anything like that, or carbon, will then the natural fiber insulators will leave that in the dust. Something that appears on a lot of these slides you'll notice is the second one there where the 2 is, the wood fiber layer. The wood fiber layer was consistent on the previous 2 slides as well. You see it here and you see it here, and on many of the slides. The reason for that is it has a really crucial role to play. It's used to prevent thermal bridging. So if you look at the bottom right-hand image there, the bottom left-hand image there, you'll see each one of those rafters would be filled with insulation. But without a wood fibre layer on the outside of those rafters, the insulation might as well not be there because all that heat is just going to conduct through that rafter, being the more conductive material. It's a separation in the insulation line, you see. So it doesn't matter how much insulation you've got in the rafter, if you're allowing the energy out through the rafter itself, you'll have a lot of thermal bridging to contend with. So wood fibre is brilliant at preventing that, where thermal bridging, is very frequent. And in timber frame construction, thermal bridging is very frequent. So if you look at this independent calculation that our friends in Waymore Architects carried out for us, you see a timber frame 2D plan view of a corner, and you see all the thermal bridging that appears in the primary frame of space itself. You see each one of those stud joists represents a heat flow path, so it's a way of energy getting out of your building. But the wood fibre on the outside of the frame prevents it from occurring. So what you end up with, if you look at the thermal image on the right, you end up with a lovely consistent blue border around the outside of that model. And if there was a little bit of yellow or orange or red coming out through that blue, you would see heat loss. That would be an indication that some heat is getting out. But that's a lovely consistent cold surface on the outside. That's because the wood fibre is keeping that energy inside the building. It's keeping that energy inside the building. It's not letting it out through the studs. So this is where the secondary layers of insulations, especially in the natural fibre context, wood fibre plays a vital role in actual performance. And when it comes to performance, the structure of the building is always at odds with the thermal performance of the building. Because Andrew Lumberg once told me it's important, apparently, for buildings to stand up. And I would agree with him on that. So if you allow these structural interruptions to simply go through your main insulation layer without resolving them, then you'll end up with a lot of thermal bridging across your building. So this is just one small section of a 3D thermal image or thermal detail that I carried out. It has cellulose between a stud frame and it has wood fibre on the outside of the frame. And the main structural interruptions would be the stud itself and the crippled studs holding up the steel I-beam and the steel I-beam itself, which is going through the main insulation layer. All of those thermal bridges are passing straight through the majority of the U value. So that grey block, that's the majority of your U value. That's doing all of the U value heavy lifting. But that's also where all the thermal bridges are. So while the wood fibre layer on the outside does improve your U value slightly, it's actually designed just to stop that thermal bridging. A secondary insulation layer can do that better than anything else. So if we just look at, if I run the model, if I press run on a model, what happens when I have wood fibre on the outside, I get a nice, consistent, cool outer surface. No heat loss is apparent coming through that detail. About something like, I can't remember the figure off the top of my head, it's something like 11% of the energy lost in that detail overall when you run it is associated with the thermal bridging. But if I take the wood fibre off and I replace it with OSB, if I just say this is a normal frame from the 1990s, I'm going to put OSB in the back of it, and I rerun my model, and then I look at what's happening, I don't get a consistent blue line anymore. Now I can see where the energy is being lost. I can see the studs, I can see the crippled studs, and I can really see the point thermal bridge in terms of the steel I-beam. So this clearly demonstrates a more uneven distribution of fabric heat loss. So the losses are more focused on those interruptions, from the structural necessity. So the wood fibre helps prevent that. And I think that the overall heat loss associated with that I-beam alone jumps by a factor of 3, just because I removed the wood fibre layer. So it really allows energy to get out of your building. This is where low energy modern buildings, sometimes they don't quite perform as well as you expect them to. That can be down to thermal bridging or can be down to air tightness sometimes. So wood fibres and natural fibre insulations they belong in the highest performing buildings is I guess the theme of this few slides. Jim, when you build this way, you end up building a very, very structurally sound, warm building. And then, of course, we got to look at the carbon, just to circle back to the purpose of today's presentation. We're going to just look at some target values just to give some figures and context for it. But if we want to look at like true zero energy buildings, we need to go beyond operational performance. We know that we should all be building A-rated buildings. But even to add to that, I think most people know now that passive is probably the building principle to aim for. Anything less than that is probably less performance. So let's just look at a couple of projects, commercial project and a domestic project, and we'll reference these values as we look at it. But if you look, like what I'm looking at specifically is the second row, the embodied carbon row. This is the RIAI 2030 climate challenge target. Okay, so this is where it's a commitment by the architectural profession to reduce operational energy and embodied carbon by 2030. So it's a great way for the industry to go, right, let's do something about our projects. But if you just look, we know that we want to get the buildings as low energy as possible, so we won't look at operational energy. But we will look at embodied carbon. For dwellings, they set a target value of 625, and for schools, they set a target value of 540. So I'm going to show you a school, I'm going to show you a dwelling. They're built with natural fibre insulations, and just reference how well it's done against those two values. So the first one is one of Leiden Design's early projects. So they'd be well-known company in this space, and they gained a reputation for building low-carbon, high-performance buildings. And this is one of their early projects, and they started small. It was 200 square meters. It featured in Passive House Plus magazine. They had some carbon assessments done, and they smashed their targets out of the water. Okay, so they defeated those targets for schools by approximately 54%. Okay, lower than for new schools. So when the concept worked, they built this school, by the way, from timber frame studs. They had a medite OSB airtight board on the inside, taped up for air tightness. The frame was filled with cellulose, and the outside of the frame used a wood fibre board before it was clad with a rear ventilated facade. So that's how they smashed their targets. Now they built the passive principles, so their operational performance is very good. But because it worked, they factored it up by a scale of 5. Okay, and they done it again. So they created a 1,000 square meter project this time in Offaly. And the value then that they achieved when they had an independent carbon assessment done was 488.2 kilos of CO2 equivalent per meter squared, comfortably beating that 2030 climate challenge target for schools. Okay, and when they looked at this more carefully with an independent assessor, they found that 1/3 of their emissions came from the concrete foundation, which they had nothing to do with. It was outside of their scope. Okay, so this is some of the figures that they got from that independent assessment by John Butler from who is a well-known whole life carbon consultant, and they found that while the as-built performed very, very well, if you look at the bar chart in the center, the as-built without the foundations would have had a massive reduction, maybe 3 times less carbon overall. So some of these design choices are out of your hands, but you can really have a big impact with some of the obvious low-hanging fruit, carbon in concrete, carbon in steel, things like that. So because they built the way they did, they more or less assured that they would beat their targets, but they can always do better. Maybe in this case, if they were given an A, they could have been given an A plus or an A plus plus from reducing the amount of concrete in the building. And the same can be true for dwellings. Now, the standard for dwellings is harder. Is a bit easier. The values that are put in the dwellings are a little bit higher. But if we look at my boss's house, Niall Crossan, for the domestic context, he built a naturally insulated timber frame to the Passive House standard. And, just through careful material selection and good design, really, that's all he needed to do to hit the ZEB standard or the NZEB standard at the time. He was guaranteed to get his A rating, but he really wanted to, especially working in this industry for so long and being so well known, he wanted to make sure that he done it in as environmentally friendly way as possible. So he built a timber frame, and he used blown wood fibre called Gutex thermofibre into a 220 frame, and he used 50 mil of Thermofleece cozy wool as an insulation for a surface cavity behind his plasterboard. And on the outside of his frame, I think he used a 60 mil wood fiberboard before building various types of rear ventilated facades on his building. So that'll give you an idea of how he built his house, right? But just to get an idea of how his house performed, we didn't look at his U values, which were outstanding, or his windows, which were as high performance as the market has, or his heating system, which is state of the art, or his insulated foundation type. We didn't look at any of that. We just looked at air tightness in his home, right? So from an operational point of view, it was recognized very, very early on that the predicted heating cost was really influenced by air tightness. Because if you've got a heat pump designed to heat a volume of air in a home, and if that home can't contain that air, then it's going to be heating more and more and more air. So depending on how many air changes it needs per hour, it's going to need more and more and more air. This is where heat pumps get a bad reputation from. So based on Niall's known volume, his known U values, his known everything, we just looked at air tightness alone and predicted in 2019 at the time that, with some evidence of degree day information in his area, the type of temperatures that he would experience annually, the type of temperature he wanted inside, the volume of air he had, we were able to look at what would happen if we made his building leakier from left to right. He got an airtight result of 0.4, which is on the left-hand side. And we predicted that at 0.4, his energy bills just to run his heat pump would be around €330 a year. And then we looked at what might happen should we make it more leaky, more and more leaky, all the way up to the building regulations at the time, which is 5. We predicted that he'd spend about 1,700 extra just based on poor airtight detailing. So from an operational performance, the U values and things like that, the type of insulation you choose is probably not as effective as air tightness. So air tightness in this case proved to be very substantially important. What we found was that when we actually analysed Niall's bills in 2025, the end of 2024, the heating cost, which was predicted, which was €328, we actually got 8% out, so 8% off compared with his actual bills. His actual bills were €302, so they were slightly less. So the performance gap was tiny in Niall's house based on predicted pre-construction costs, just based on good design detailing, good U values, etc., based on what he's actually spent to date to run his heating system. So just good design and following passive principles can lead to this level of tiny performance gap. And then I suppose there's nothing like lived experience to just prove the concept as well. But during the 2025 winter power outage, when a lot of the country had no energy for long periods of time, Niall's house kept a very steady temperature of 19 degrees. So it was clear it could hold that energy. He was able to walk around in the house for, I think it was over 2 weeks with consistent, nice, warm temperatures in his house just from good solar gain during that period, and with consistent temperatures around 19 degrees. I know my house certainly wasn't like that anyway. So when it comes to operational performance, it was no problem. Just good design detailing, good air tightness, good window selection, good U values. But that didn't mention anything about the type of insulation that was used. We just know it was a good U value. It could have been a good U value based on mineral wool or PIR or whatever. And the good design detailing would get you that low operational performance, and you'd end up smashing the targets. But what about the embodied carbon performance of your building? So this is the other half of the puzzle. This is the blind spot of the construction industry if you're not addressing it. In Niall's house, he had his assessment, and again, our friends in Wainmore, the architects, carried out the assessment for Niall and gave Niall an A rating for his home based on an upfront carbon total of 288 kilo of CO2 equivalent per metre squared. So that's nearly 3 times less than the target set out by the RIAI. Okay, so I mentioned at the start, he just done it with blown wood fibre, a timber frame, wood fibre used on the outside of the frame, and sheep wool. Okay, so he smashed his operational targets just by good detailing, but the careful selection of material gave him an A rating and helped him smash his embodied targets. But just like the Light and Design School, you can always do a bit better. You can always push it a bit harder and move it up that ladder to A plus or A plus plus. And how would you do that? Well, you look at embodied carbon figures and you find out where there is space to improve. So if you look at Niall's house, for example, the external walls made up a disproportionate carbon. The substructure, which is foundation, made up an equal amount of carbon. The roof made up this amount of carbon, okay? But if Niall wanted to do better and move it up the ladder a little bit, the walls aren't going to change. He's got them about as well as he can get them, okay, for now. If he used GGBS in lieu of concrete, he could dramatically reduce the amount of carbon associated with the concrete in the building. And then the roof is not going to change. He's still doing a good job on the roof. Likewise, he could do something with the walls. If the substructure was GGBS, and instead of blockwork on the outside, he used a rendered cement board, he can reduce the amount of carbon in the walls dramatically. So his walls were actually performing pretty good, but he could have performed even better if he didn't use blockwork as an outer leaf, but there was some local planning restrictions in place. So really, the natural fibre installations is the only things he's not having to change. He's changing things like concrete and blockwork. He's not going near the frame. He's not going near the wood fibre. The roof stays exactly the same, insulated with wood fibre, insulated with fibre. So you can really see that the impact to get it from that A to A plus plus is really about looking at the massive materials in the building, the concretes, the blockworks, things like that, which would be the equivalent of 6 years operational energy in Niall's house as a saving, or driving in his electric car 185,000 kilometers. So I think I just kind of more or less blasted through that. I think I might be a bit ahead of time, but thank you for listening. And if anyone has any questions now, I'm happy to try and answer them. Or if you'd like to get in contact later, or for information about your CPD certificates, please feel free to contact the email address on the screen. And thanks again for listening.
Joe, that was fantastic. It really was. Yes, definitely a whistle-stop tour. I know there's a few questions in the box for you there, which I think Joey's going to look after. So Joey, if you can hear me, if you want to have a look at those questions, and between yourself and Joe, come back and respond to them, that would be very much appreciated. And if Joey isn't there, I can go through them myself with you, Joe, and call them out to you. There's Joey there now.
Yeah, no, I'm here. Yeah, so the first question, Joe, can you use natural fibre insulation in a new block build?
You can do. You can use it in. So they all have to still comply with Part D of the Irish Building Regulations. So they need to be CE marked and fit for purpose for their given context. So you wouldn't put wood fibre, for example, into beneath a screed, or as long as your sheep wool is being rolled into an attic instead of inside a cavity wall or something like that, then it's the correct application for the product. But yeah, you can do in a new build. You can put it into your attics. You can put it into your intermediate spaces for soundproofing or between floors and things like that.
Thanks, Joe. And the next one is, someone is interested in fire rating of these natural products, i.e. what fire retardants, if any, are applied / mixed in? Yes,
so they do. They all have, it's like a baking soda, and it's a 1% salt additive, which helps the product to char instead of just taking off in the event of a fire. They all are Class E in terms of their fire rating, but then depending on the assembly you use them in. So for example, in Niall's house, you can get an REI rating of 90 minutes based on his construction, or in the Eco Cocoon frame with clay inside on the inside of it, you can get an REI rating of 120 minutes. So they can, and then the straw itself is the best one to think about, because straw is often thought of as, Jesus, that not flammable, excuse my language. But if you, the way it's compacted means there's no oxygen available for combustion, and then its heat capacity means that temperatures internally never reach that high point where it can actually burn. And then the clay itself turns to porcelain in the event of a fire. And then the natural silica content in the straw is also very good as a retardant. So a lot of these natural fibres, like wood and stuff like that, they tend to char, they tend to blacken. But if you peel behind the surface, you get a lot of fresh material. They don't really burn very, very well. So the under fire test conditions, they tend to perform extremely well. And especially with heat, you don't get a lot of heat transfer through them. So even if something is on fire on the other side of it, you can put your hand to the back of a piece of wood fibre for long periods of time. Not that I encourage anybody to do it, but sometimes we do it. Sometimes we do it in ecological building systems. We break out the blow torches and we get people to hold on to the wood fibre and stuff just to show them the effect that it has. And it'll blacken and smoke and char. But then when you take away the flame, it tends to die out and the back of the board is still cool. For now, everything has its breaking point, but just to give you an idea. But it performs really well. Most natural fibre installations are the same.
Very good. Just another question here, Joe. When I was applying to the SEI retrofit grant scheme in 2022, I wanted to use wood fibre external insulation, but I was told by your company that it didn't have NSAI certification at the time and therefore couldn't be permitted as part of the materials for the insulation. Presumably that's no longer the case.
It depends on the requirements of the scheme. So if you have an SEI scheme that has, and it has outlined a real clear requirement for an agreement approved system, well then unfortunately you have to look to agreement approved systems for qualification under that direct grant scheme. So wood fibre is accepted in other grant schemes. So for example, if you were going for a heat pump grant and then you had to get your U values down to a certain value, it doesn't matter what insulation you use as long as they're Part D compliant in the building. Or likewise, if you want to apply for the traditional building scheme, which is it's a pilot program, they will accept products like wood fibre or other similar natural fibre products based on hygrothermal modelling to the appropriate standard, EN 15026. So it just depends on the requirement of the actual scheme. But the directly rendered external wood fibre that we would have been referring to when we answered that question is not something we promote in Ireland, just based on the fact that we live in a really, really wet climate. And that ETIC system kind of is produced in Germany. It's kind of suited more to their environment. So as a cautious approach, we try not to promote it, if that makes sense. Like we're, instead of trying to sell more of it, we're trying to protect people against what might happen if the render goes, or if there's a crack behind the windowsill, or if there's a bad seal at a window or something like that. So I'm not surprised we would have advised you against it at the time. I'm glad to hear someone did that.
Yep. Just the last one, Joe, for the moment. At Niall Crossan's house, how are the cantilever shading devices fixed to the structure, avoiding thermal bridging?
It's a really good question. So he used, we have a thermal break solution called Warmotech Phonotherm. And Warmotech Phonotherm is it's a thermal break insulation. It's made from upcycled polyurethane. So it takes things like foam from steering wheels and car seats and manic boards and things like that, and it compacts it into a really strong insulation, a bit like timber that you can machine, but you can situate it between steel plates and it compresses really hard. So it has a really strong compression resistance, 7,000 kPa. It's about 50 times stronger than the average floor insulation. So in many cases, that cantilevering that you saw would have been broken by a product like Warmotech Phonotherm to stop thermal bridging through the frame. But was well spotted. Whoever seen that?
I think that's all the questions.
Yeah, I hope that answered it.
Thanks a lot, Joey, and thanks very much. Sorry, someone with the hand up there was Nevin. Nevin, do you want to come in and ask a question?
Sorry.
Then?
Yeah, thanks very much, Joe. Thank you. Very, very interesting presentation. Just,
Thanks.
Joe, in the context of, say, dry lining a traditional stone-built building, I've seen some of your detailing there online. Where you have, say, wet rooms and bathrooms, are the natural materials appropriate in that setting? And would you be applying some sort of tanking to the inside of those natural materials?
Depends on the context of the wall. So dry line would only really be recommended if the wall has a render on the outside. So let's say, for example, we take a stone building and it has a lime render on it at 20 mil thick and it's in good defect-free dry condition. Well, then I could make a case for a dry line on the inside. And then if it was...
Sorry, Joe, sorry, just to clarify. Yeah, in this case, it's not possible to render it on the outside, and it's a wet wall. It's kind of wet, there isn't actually render on it as such.
No, I wouldn't dry line it then with a frame and organic insulation, because just take away the organic insulation for a moment and think what might happen if you just put wood again. If you tacked a skirting board onto that wall over a period of time, when you'd come back and you'd see the condition of the skirting board, it would be, the nails would be rusted, the skirting board would be a bit mushy after 5 years. It'd be the same for any insulation you put inside a wooden frame or in the frame itself. So in a scenario like that, I'd be more inclined to promote the use of a mineral-based product like lime on the inside of your wall or calcium silicate boards bonded to it. And then that will allow the wall to dry rapidly. You don't have any organic content in it or anything that's compostable. And then you can also consider tanking that to a certain height, waterproofing it and making sure there's no water penetrating into the product and into the wall from the shower itself. So we can help you with that detail if you get in touch.
Okay,
I can give you an actual specification for that, no problem.
Okay, thanks, Joe. Thank you.
Oh, you're very welcome. Thanks, Nevin.
We have a couple more questions just come in there, Joe. So it's just someone is just looking for the start to the presentation. I'm fairly sure it has been recorded, isn't it, this presentation, Paul? You might be able to answer that.
Yeah, it's recorded and it'll be available on the MMC Ireland website. So there's no issue with that. And I'm not sure whether if you want to share your PowerPoint presentation, Joe, and we can stick your email address at the end of this presentation for people to get in touch directly.
I think I'll have to have a chat. See, this is still a work in progress, and there is some information in it that I'm not sure about permission. Some of it definitely could be shared, and you can put it up online, no problem. But when it comes to the actual PowerPoint content, I'm not sure about that. I'll have to double check that one.
No problem, Joe. The actual recording itself will be on the MMC Ireland website from tomorrow.
Thanks,
Great.
Paul. Just another question there, Joe, for yourself. Are GGBS foundation solutions widely available in Ireland?
Yeah, I think a lot of companies are under pressure. Not just like, I think a lot of companies are really innovating in this area. It's not our direct game like GGBS, or I think it's ground granulated blast furnace slag is, Paul, if I'm not mistaken. But it's GGBS is like a low impact kind of cement, but there are other types of cement also emerging that are using different types of aggregates as well that are really reducing the content. But I would say the best place to go for that type of confirmation would be the IGBC. So the Irish Green Building Council, they would have platforms for environmental product declarations, and a lot of these products would have their information listed through that platform. So EPD Ireland. So I'd maybe make a start there, and you can certainly specify a lower carbon concrete, for example. I know Cairn Homes have recently looked into this, and other companies as well, other large developers. So it's a big impact area.
Very good. Joe, I think that's pretty much, there is a question there from Nevin, but we've answered that. And Nevin has also requested your email address. But Nevin, if you want to get in touch with just info and put the attention of Joe on it, it'll just fly straight across to him and he'll get back to you that way.
Yeah, absolutely. I think Paul has a question there. 600 stone wall, which has EWI externally. It's currently sand cement rendered. Then rendered internally, then dry lined, some slight evidence of moisture internally. What would you recommend internally in relation to insulation, boarding and render? Can strip back all? Yeah, I would normally say that without knowing the building too well or seeing the building too well, when you mention cement on an older building, and I could only encourage you to take off cement on an older building. Generally speaking, that helps to improve things really quickly. So that gives the building a chance to, without triggering anybody, breathe. That's a word that can be used. But it's I think usually when you remove a layer like that, then you have to ask yourself what's going back in place. And that's where lime or lime-based products makes a lot of sense. Again, we have a lot of options for that, and so do other companies, just so it's not a shameless sales answer. Lime is generally appropriate for old walls, and if you use lime on old walls or lime-based products on old walls, you'll generally get good outcomes with good drying capacity.
I think that's it, Joey.
That's it. There's no more loading for me here, so that's it, I think.
Let's see, Lasha has the hand up there. Go ahead, Lasha, if you want.
Hi, dears. Once again, Joey, thanks for your presentation. It was awesome.
Good,
so, guys, it's for my thing. I'm reaching you from Georgia, Tbilisi. and I am interested in the field of straw bale panels building.
Mhm.
About 2 years ago, I have built my own house with the straw bale panels, and during this time, I have came across an idea that why not introduce this type of buildings to the society and to start somehow doing the thing. My only need for you is that I'm at the moment I'm on the level where I'm going to gain some kind of networking with the people who have more experience than me. And if anyone wishes in this group, maybe you can leave your email and I will get in touch with you, send you the story of me, send you the picture materials maybe. So this is my ask, and thank you.
Thanks, Asha. That's great. Best of luck with your
Thanks,
house.
Lasha. But Joe, thank you so much for that. That was like hugely educational for me in particular, having not been an expert in this field by any stretch. And I want to thank you and the team for an excellent presentation and genuinely some brilliant answers to some really tough questions. It's certainly the technical detail that you've gone into on your answers were top class, and that's represented by the feedback in the chat room. So thanks a million, Joe. Thanks, Joey. Thanks, Emily. Anna, thanks again on behalf of MMC Ireland. And thank you all for joining. If you follow us on LinkedIn, which I'm sure most of you do, you'll see the notice for next month's Lunch and Learn. We'll carry these on throughout the year, and it's the fourth in the series. We have a number of them lined up for the next number of months. They've proven to be very successful and informative for people in the industry. So thank you all for joining. I really appreciate taking an hour out of your day.
Thanks, Paul. Thanks, guys.
Thanks all. Thank you.
Chat to you soon.